Alright, so in this video on entropy, we're going to talk a little bit about the Carnot cycle, okay? And we're going to use this cycle to, one, show the fact that entropy is in fact a state function, but to, two, be able to kind of relate this then with heat engines and efficiencies of heat engines and things like that that we would think about in kind of engineering applications, okay? And that will then also then be related with the Clausius inequality, okay? Which we'll talk about near the end of this video. Okay. So, right, we stated that entropy is a state function, but here we're going to show that in fact it is a state function by showing that if I do a cycle of something where I eventually end at the same place I started, the total entropy change will be equal to 0. Okay, and so this is demonstrated through what is called the Carnot cycle. Okay. So how the Carnot cycle works is I'm first going to do a reversible isothermal expansion of my gas from A to B. I then do a reversible adiabatic expansion from B to C, a reversible isothermal compression from C to D, then finally a reversible adiabatic compression from D back to A, right? So again, you know, looking at kind of the figure here, okay, on the right, you go A to B, B to C, C to D, and D back to A, right? So eventually we end back where we start, okay? So the question is what is the total entropy change for this process, and what is the entropy change for each individual step, okay? Well, for a reversible isothermal expansion, okay, right, everything we've talked about, right, in this Carnot cycle is done reversibly. So everything's done reversibly, right? So the heat transfer is the reversible heat transfer, okay? Well, an isothermal process, right, for reversible isothermal, we know the heat transfer is just minus NR, is just equal to nRT ln V final over V initial, okay? Because for an isothermal process, for an ideal gas, Q equals minus W, okay? And so the entropy is just that reversible heat divided by temperature. So temperature goes away, right? And so for step one, the entropy change is just NR ln V final over V initial, okay? For step two, and I have a reversible adiabatic process, well, that's easy, right? For an adiabatic process, Q is equal to 0, so the entropy change is equal to 0 for this process, right? Then for step three, I do a reversible isothermal compression, okay? Again, it's a reversible isothermal, so the entropy change is going to be minus NR V final over V initial here. Now note I have V4 over V3, these are different volumes, okay? Than the initial volumes in step one. And then I can do a reversible adiabatic compression, which again, is just going to have an entropy change of equal to 0, because it's an adiabatic process, and it's done reversibly. Okay? So, our total entropy change then for this Carnot cycle is delta S1 plus 2 plus 3 plus 4, right? Which is NR ln V2 over V1 plus 0 plus NR ln V4 over V3 plus 0, right? Which gives us the total entropy change is NR times the natural log of this ratio of volumes, okay? So the question is what are the ratio of those volumes, okay? Well, we know for an adiabatic reversible process of an ideal gas that those changes in volumes are related with the change in temperature, okay? Well, and so for steps 2 and 3, so this is, right, this was steps 2 and step 4, sorry, right, steps 2 and 4, I did an adiabatic process. So when I went from volume 2 to volume 3, and then in step 4 here, I went from volume 4 to volume 1, okay, right, these changes in volumes are going to be related with the changes in temperatures, okay, right, isothermal processes didn't have a change in temperature, temperature changes in the adiabatic process, okay, and these temperatures were labeled as hot and cold, right, and so these ratios of volumes are related with the ratio of temperatures, okay, to the CV over N hour power, right, okay, and note here that the ratio of these volumes are equal to the same thing, right, that V3 over V2 is equal to TH divided by TC to this power, and V4 over V1 is the same thing, right? So if I look at this product of volumes, right, I can see that V2 over V3, or sorry, V4 over V1 equals this. I'm going to call this, say, X, right? and V3 over V2 equals X, right? Well, I have V2 over V3, so this just equals 1 over X, right? And so I have X for V4 over V1 and 1 over X for V2 over V3. So those things multiply together because it's X divided by X, which is equal to 1. So this is the natural log of 1, which equals 0. So the total entropy change for this process is equal to 0, okay? Because the natural log of these ratio of volumes is equal to 0. Because the ratio of those volumes is equal to 1 for a reversible isothermal process, okay? Therefore, this entropy is a state function, okay? And in the next video, we'll talk more about the kind of work done in this process and efficiency of the process, and talk about the Clausius inequality.